Welcome to Module 1, Part 3. In the previous part, we have seen the biasing in the BJT amplifier. Basically, we have seen two types of biasing in BJT amplifier. First one is voltage divider bias, and the second one is biasing using collector to base feedback resistor. Then we have seen the derivations of the collector current, the transconductance, the base current, the emitter current, and the voltage gain. And we have also seen an hybrid pi model. Next, we are going to check the biasing in MOS amplifier circuits. Basically, there are three types of biasing in MOS amplifier circuit. First one is biasing using biasing by fixing VGS, biasing by fixing VG, and the third one is drain to gate feedback resistor. So these are the three types of biasing. So let us check one by one. This is the circuit of biasing by fixing VGS. So over here VGS is fixed, the gate to drain voltage is fixed. So biasing is done basically to have a to select an appropriate DC operating point such that the MOS transistor will operate as an amplifier. So this is done such that the drain current ID should be stable, the ID current should be stable, and the VDS voltage should be stable. So VDS voltage is over here, VDS. So this is the emitter terminal, gate terminal, and the drain terminal. VDS voltage is at this point. To select an appropriate operating point, the drain current and the VDS voltage should be stable. So that is done by biasing, that is done by fixing the VGS. So this method of biasing is not an appropriate method. So with this, we may not obtain a constant ID or a stable ID. So let us check what happens. In this case, the ID current equation is given by this. In this equation, the oxide capacitance, W by L ratio, and the threshold voltage Vt changes from transistor to transistor. Even the transistor is of same type and manufactured by the same company, these quantities vary. The oxide capacitance, W by L ratio, and the threshold voltage varies. Along with this, mu n and the threshold voltage Vt vary with temperature. So any small change, variation in the temperature, these quantities will vary, as a result of which the ID current will vary. So even after fixing this VGS, because of the variation in the temperature, the ID current will vary. So this ID will not remain constant. So this method of biasing is not an appropriate method or not an efficient method. Let us check a graph of ID versus VGS. Now here if we check, so this is the characteristics of two devices, MOSFETs devices manufactured by the same company. If we fix the VGS over here, check out the variation in the drain current ID. This variation is mainly because of the threshold voltage Vt, mu n, oxide capacitance Cox, W by L ratio. They all vary even when VGS is constant, and you get the characteristics in this particular manner. So here you can see large variation in the ID current. So ID varies, it is not stable. Hence, this method of biasing is not an appropriate method. So another method of biasing the MOSFET to select an appropriate DC operating point is by fixing the gate voltage Vg. So biasing by fixing Vg is done by keeping the Vg, the gate voltage constant, and connecting a RS resistor in the source terminal. So this is the source terminal, the gate terminal, and the drain terminal over here. So when we have a resistor uh, RS in the source terminal path, now we have the voltage Vg, then we have the gate to source voltage. Apply KVL in this particular path, so we get Vg minus VGS minus ID RS. The current flowing through the source terminal and drain terminal is same, that is ID. So solving this, we get this equation Vg. Vg equals to VGS plus RS ID. Now we will check how the ID will remain constant by fixing the Vg. Now if in any case, if we consider Vg to be far greater than VGS, Vg is greater than VGS. So in this case, Vg is constant, so it is made far greater than VGS. So in this case, VGS will be a negligible quantity and ID will be equal to Vg by Rs. So both are constant quantities. Vg is made fixed, it is fixed. Then Rs is a constant. So as a result, ID will remain constant. Now the second case, when Vg is less than VGS. If by any case Vg is fixed but it is less than VGS, then in that case the RS, the source resistance RS, will act as a negative feedback, and then it will bring down the drain current ID, and as a result the drain current ID will remain constant. In a more detailed way, assume for any by any chance the ID will increase. So if ID increases, Vg is fixed. Vg is already fixed. So this quantity should be equal to Vg. By any chance, if ID increases, then Rs cannot be changed. Rs is fixed. So Vg has to vary such that this quantity will be equal to Vg. So this quantity has to decrease. Since ID increases, Rs cannot be varied, VGS should decrease to make it equal to the quantity Vg. So Rs is a regenerative resistor over here, or it acts as a negative feedback, and as a result of which the VGS will decrease. Since VGS decreases, the ID will decrease. So as a result, the Vg, or by fixing Vg, we can have a stable ID. If you consider the ID VGS characteristics of these two devices, Vg is fixed. This is the device characteristics, which is represented by a slope over here. which indicates the constraints by the biasing circuit. Now Vg is fixed over here. We can see the ID current of two devices is almost equal, very close as compared to the previous case. By biasing by fixing VGS, the ID current was different. There was a large variation in ID current, but over here the ID variation is very less, almost equal, very close to be equal. Hence, this method of selecting a DC operating point is an appropriate method. Next, we will check the third method of biasing the MOS circuit. The next method of biasing the MOSFET is by using a drain to gate feedback resistor, that is RG. The RG, or the drain to gate feedback resistor, is very high. As a result, no current flows through this particular path. The entire current flows through this path, through the drain and the source. So this Rg, the large value of Rg, makes the gate current VGS and the drain current equal. VGS is equal to VDS. Now, since no current flows through this path of Rg and the gate terminal, the entire current flows through the drain terminal and the source terminal. If we apply KVL at this particular path, so it will be VDD minus IDRD minus VDS is equal to 0. Now VDS is equal to VDD minus IDRD. Since VDS and VGS are equal, VGS is equal to VDS, which is equal to, from this particular equation, it will be VDD minus IDRD. Now VDD from this particular equation is equal to VGS plus, so this comes over here, VGS plus IDRD. Now this equation is similar to the previous equation where we checked in the biasing by fixing VG, where VG was equal to VGS plus IDRS. Now VDD is fixed. If by any chance ID increases, then to make this term quantity equal to VDD, any one of the quantity should decrease since ID has increased. RD cannot decrease since RD is fixed. In that case, only VGS has to decrease. So if VGS decreases, automatically ID will decrease. So this brings the ID quantity to be stable. So this is the third method of biasing. Basically, we are trying to stabilize the ID current, by which we can also stabilize the VDS voltage. When these two quantities are stable, then we can select an appropriate DC operating point, by which, by selecting an appropriate DC operating point, we can see to it that transistor operates in the saturation region in which it can operate as an amplifier. So these are the three methods of biasing the MOSFET. So let us take an assignment problem. You have to design this particular circuit. Drain to gate feedback resistor is connected over here, RG. The drain current is given ID 0.5 milliamps. Assume VDD. This VDD is 5 volt. Threshold voltage is given 1 volt. Lambda 0. Lambda is assumed to be 0. Use the standard 5% resistance value for RD. So RD can be selected a particular value and give the actual values obtained for ID and VD. So the actual values you have to calculate for ID. Earlier value given is 0.5 and VD is given. Now we have to find out the actual values. Kn dash W by L ratio is given for the ID equation which we have considered in the first slide. Kn dash is mu n Cox. ID is half mu n Cox W by L into Vgs minus Vt the whole square. For that particular equation, these values are given. So you can substitute ID over there and get the value of ID. Then from the previous slide, you can get the equation for RD to calculate RD. VDD equals to VGS plus IDRD. You can take that equation and calculate the value of RD, ID, and VD. So this is the answer. Do the calculation and see that you get these answers. Thank you.